Hello, welcome to Aliens Space Education. We have a fantastic episode for you today on the life cycles of stars from birth to death. Now, we're only going briefly into the life cycles, so the fundamental building blocks of the universe, and understanding them helps us comprehend broader workings within the cosmos. From stellar birth in a nebula to the dramatic deaths of a supernova or a white dwarf star, and going through their incredible transformation. So let's get started on this exciting, fascinating journey of the stages of stellar evolution. Now, just like humans, stars are born in a nebula. They go through a process, they get older, and some grow bigger, some don't, depending on what happens, and eventually they die. And the cycle starts all over again. So very much like humans, we go through different phases of our lives, and the stars have this. So this is how we see it and how we understand it. So stellars start off in a stellar nursery. This is where the stars are born. So just like a human getting pregnant, this is the beginning stages, and they're born in what's called a nebula. This is where a vast dust and clouds all combine and mix together to make a region. That includes 3 different types of nebula, and these are the ones we have seen. Okay, so most common ones are emission nebulas. These nebulas emit bright light due to ionization of the gases by ultraviolet radiation from nearby hot stars. And because of that, they're really bright and we can see them. And the best example of that is look for the Orion Nebula. So if you know where Orion is, look for the nebula there. This is a classic example of an emission nebula. Okay, the next two, a little bit harder to find if you know what you're looking for. Okay, reflection nebulas. These nebulas do not emit their own light, but they reflect light from a nearby star. So they're only visible if there's lots of stars or a star nearby they can reflect the light from, and they are not as common as you think. Emission nebulas are the most common ones. And they emit their own light, but reflect light from nearby stars, and they often appear blue due to the scattering of shortwave wavelengths. So if you see a nebula and it's more blue, it's a reflection nebula, whereas an emission nebula is ultraviolet. So there's a big difference between them. However, there is a third type which is even harder to see. These are called dark nebulas. These nebulas do not emit their own light, but reflect light from... No, hang on. These are dense clouds. This is my mistake. I read the wrong line. My apologies. These dense clouds of gas and dust that block light from objects behind them, creating dark patches against the background stars. Now, when we look at the stars and we see a dark patch, that could be a black hole, or it could be a dark nebula, or it could be nothing there. We don't know. Now, we recognise black hole because when it eats a star, we see the light emitting from it. But if the black hole isn't eating anything, we don't see it. So dark nebulas are very, very hard to find. But this is generally where stars are born, within one of these 3. The birth of stars starts when the region within a nebula goes into what's called a gravitational collapse. So you think, like an earthquake, it collapses in. It's pulling everything in. As the gas and dust clump together, something's got to catalyse that thing. So something makes it all collapse and pull together, and then they come together and they form what is known as a protostar. So think of someone being pregnant, think of it being pregnant, and the protostar core begins to heat up due to the pressure of the collapsing material. As the core reaches temperatures and pressures high enough, nuclear fusion begins, making the birth of a new star. So all this time, when it's all coming together and everything like that, it's growing bigger and bigger, it's getting hotter and hotter, and eventually, the star is born. We get a brand new star. The process of star formation can take millions of Earth years. Now remember, we do this in Earth years because we can't do it. It's the easiest way for us to understand. So over millions of years this can take. During this time, the protostar continues to accumulate more mass from surrounding material, so it grows bigger and bigger. It keeps eating and eating and eating. And once nuclear fusion is established and the star enters what's known as a main sequence phase, which is the main common phase we see, like our sun, that's where the sun will spend most of its life. Just like we do in our life, that's where the star does. When we're living, it's where we are. Okay. It's really cool that the stars have the same sort of sequence. Very different. Now, making sequence stars, the longest phase, varies depending on the type of star. So its formation, a star spends most of its life in its main sequence. It fuses hydrogen into helium in its core, processing energy that makes the star shine. So it's this hydrogen into helium that makes the star bright. Now, depending on the size of the star, depends on how much hydrogen there is, how much helium it can produce from that sequence, and then how long it will live. So the star mass, which it comes down to, there are three types: high, medium, and low. So let's start with the bottom one, the low mass. These stars are like our sun but smaller. They have a lifespan of about 10 billion Earth years, so they've been around for a really, 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 really long time. They can last longer. They burn their hydrogen extremely slowly. Remember, the hydrogen is getting burnt up extremely slowly, turning into helium, leading to long periods of stability, and often blue. They're often blue in colour, well, reddish sort of things, because they're still, even though they're burning, they're small, they're cold. As the star gets bigger, remember from previous episodes, blue is hot, red is cold. So the low mass stars tend to be more reddish, but they can go blue depending on thing. But because they're small, the mass is small, they can still grow quite bright. Medium mass stars are more like our sun. Our sun is a medium mass star. It has a slightly more mass. Its lifespan is between 5 to 10 billion years. And this is exactly where our sun fits. And at the minute, our sun is about 5 billion years old. So we're dead center in the middle. That's where we are. And eventually, when our sun burns out of its hydrogen, it will, just like all the other medium mass stars, evolve into a red giant. That's a big step. It's 5 billion years away when it grows bigger and bigger, and it'll grow really, really big. So you got to think that's a long way off for us. A long way. It's 5 billion years away. So we've got a long time to go. But remember, they live for about 10 billion years. Okay, high mass stars. Now these are the big, big ones. They're more bluish in colour, everything like that. These stars are, which are even bigger than the medium mass stars, more than 8 times bigger than the mass of our sun. They're massive. But because they're so big, they have a shorter lifespan. They only last a few million years because they're burning the hydrogen off more, faster. Because it's so big, there's more hydrogen getting burnt up. They burn through the hydrogen more rapidly, move through the different stages much more quickly than the low mass counterparts. So depending on the star, the low ones live longest, the biggest ones live the shortest. Okay, the main sequence phase characterized by a stable balance between gravitational forces pulling inward and radiation pressure from the nuclear fusion pushing outwards. This equilibrium keeps the star stable, shining bright for millions or billions of years depending on the size of the star. So it's really important that we look at the gravity that's pulling it in and the radiation pressure of nuclear fusion pushing it outwards. So it's a very careful balance. Red giants is a star's aging process. So it's when a star reaches old age. As a star ends their main sequence, they may exhaust the hydrogen fuel from the cores, which marks the start of the red giant phase. In this stage, the core contracts under gravity, so it's being pulled in. Remember, nuclear fusion is pushing out, causing the outer layers to expand because nuclear fusion is pushing out. So even though gravity is pulling it in, it's creating more heat, more energy, so it's expanding outwards. The outer shell is expanding bigger and bigger and bigger, going much larger and much redder as it transforms into a red giant. There are 2 outcomes from a red giant phase, depending on the star mass. So it could go either way. So low to medium, stars like our sun, so which remember we're a medium star, will eventually shed the outer layer, creating a planetary layer. The remaining becomes a white dwarf star. Now I'm going to cover white dwarfs a little bit further down, so please don't worry. Which is a hot, dense remnant that gradually cools over billions of years, but it creates a nebula. So once a red giant ends, all the gas, all the heat, all stuff that it didn't use gets sent out into a nebula, into a giant dust cloud. The remains of the outer layers become dust, and that's what creates a nebula. But the remaining little bit in the middle, this tiny little white dwarf star, a tiny little star will remain in the middle at the very centre. Whereas a high mass star, so that's low medium, the high mass star, these stars undergo more dramatic changes. They expand into supergiants and begin fusion of even heavier elements in their core. So we're talking a lot more complex elements getting burnt up, getting created, getting sent out into the universe. The lifespan of the high mass ends in, the only way to describe it is a massive explosion, or as you know, a supernova, a spectacular event that disperses all these heavy elements, all the elements it creates, out into space. And they collide with nebulas and then create the cycle of life. So all these elements are all mixing together to create, but the supernova expands, it blows them out miles and miles away. The material ejected from these events enriches the interstellar medium with heavy elements, which can then be incorporated into new stars and planetary systems. So these heavy elements are crucial to life. So we need supernovas to happen, so we get these high-rich materials. It's incredible that depending on the size of the star, it even affects us here. And we're tiny when you look at the size of a star. Remember, the sun can fit 1,200 Earths inside. That's 1,200 Jupiters inside, but Jupiter can fit 1,000 Earths. So it's over 1 million times the size of Earth. The sun is 1 million times, can fit 1 million Earths inside. That's how big the sun is. And without these stars growing bigger and everything like that, these things wouldn't happen. So we're tiny. White dwarf stars and neutron stars are the remnants of stellar evolution. Let's take a closer look at the remnants after their dramatic phases. White dwarfs, these are remnants of low and medium stars. After shedding their outer layers and leaving behind a planetary nebula, the core cools and contracts into a white dwarf. So even though it's still a star, it's still really, really hot. It still contracts into a tiny little ball because the radiation pressure going out has gone. So it just contracts under gravity and just makes a little glowing ball, which is the mass of the sun. So you think how big the sun is, condense all that mass down, compress it all down to the size of the Earth. That is a white dwarf star. Really small, but really, really bright. However, over billions of years, because the radiation isn't pushing it in and helping it glow and that, over billions of years, it cools down and eventually fades away. So it takes a few billion years for it to cool down. So even though it's lived for up to 10 billion years, after that phase, it can still glow for a few more billion years before it glows down completely and cools down off. And it doesn't produce any lights. Neutron stars, however, are the remnants of a high mass star that have undergone a neutron star, a supernova. The neutron stars are the remnants of a supernova. Neutron stars are incredibly dense. They have a mass about 1.4 times that of the sun, but a diameter of about 20 kilometers, or about 15 miles, give or take. So you think 1.4 times Earth, the sun, 1.4 times bigger, but within 20 kilometers. And they spin super, 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 super fast. Neutron stars are incredibly, but they're really condensed, really heavy, so that's why they spin so fast. We're watching them. The core consists mostly entirely of neutrons. And neutron stars have a strong magnetic field. And like I said earlier, spin really fast, rapid rotation. Some neutron stars are observed as pulsars, and they're making regular pulsars of radiation. So they're sending out beams of pulses of radiations. The pulsar stars are neutron stars. In some cases, if the remaining mass of the core is even greater, it can sometimes collapse. Now, these are high mass stars. These are the big stars, not ours. The big stars can collapse into black holes. Now, black holes are regions of space where gravity is so strong that nothing, not even light, can escape their pull. It's all pulled in. Everything is pulled in more and more and more. And the boundaries of the black hole are called the event horizon. And the event horizon is where we'll see a disk of glowing material or star get pulled in or anything like that, and that will shine bright, and that's how we know it's a black hole. It's because of that, the edging. Beyond that point, the gravitational pull is irresistible. So once it gets into the event horizon and gets pulled in, that's it, it's gone. You will not see it again. So really, really dangerous. But what are the roles of all this? Well, in the role of supernova in the universe, supernovae, as it is, are not just spectacular explosions. We do like to watch things blow up. Boom, big explosion in the sky. Yeah, lots of fun. However, you watch fireworks and things like that. That's it. But they play a crucial role in the universe. They play a critical role that we really need to know. These events are responsible for creating and dispersing many of the heavy elements found in the universe. So the giant stars, these massive stars, create all these heavy elements, and because they explode in a supernova, it pushes them out into the universe, and that's where we get them from. When high mass stars explode in supernova, it releases a tremendous amount of energy and ejects the outer layers in space. This process not only enriches the interstellar medium with elements like iron, nickel, and other elements, but also triggers the formation of new stars and planetary systems. So remember at the beginning when we talked about nebulas, I was saying that the stars have to collapse, so something has to happen to get gravity to pull everything together. It's a supernova, and that's what I wanted to wait to hear. It could be a heavy element or something like that affects the gravity that pulls the things in, and so the cycle begins. The remnants of a supernova can also lead to the formation of neutron stars or black holes, depending on the mass of the original star. Now, even though we're talking about super heavy giants and things like that, it doesn't always mean a black hole, but it could mean that there's a black hole and a neutron or a neutron star. But generally it goes either a neutron star or a black hole. Can't say which way, but generally it's one or the other. These remnants can influence the surrounding environment and affect the formation and evolution of nearby stars and galaxies. The reason we say that is because at the center of every galaxy we've found, there's a black hole. So there's a big black hole there, spinning around, pulling everything in. That'll take billions, trillions of years before we even get close to it. But it's happening, and there are black holes within our own universe, in our own galaxy, and we're still discovering. So supernovas are essential to the cosmic cycle of matter. They're crucial to us. They contribute to the ongoing process of star formation and evolution of the galaxies. Because as stars collapse and die, they send more material out, which means new planets can be born, new stars can be born, and the cycle begins all over again and constantly goes round and round and round. Like I say, they don't always turn into a neutron star or a black hole, but the cycle takes billions and trillions of years to happen. Star evolution and galactic ecology, understanding the star's life cycle is key to understanding the broader process, the shape of the galaxy and the universe. Stars are not isolated entities, part of a dynamic and interconnected system. Just like we are, as we live and die, we are part of an interconnected system. Stars are the same, but they're on a bigger scale. The cycle of stars, birth, evolution, death, just like humans. We're born, we evolve, we grow big, we go from child to adult to grandparent to old age people, and then eventually die. We go through the same sort of cycle. There's very much similarities, and we're made of star stuff, so it's got to come from somewhere. This all contributes to the galactic ecology, influence the formation of new stars, distribution of elements, and the structure of the galaxies, because they will influence how galaxies turn and everything like that. The material expelled by stars enriches the interstellar medium, providing building blocks for future generations of stars and planetary systems. Just because it happens there, it could take millions of years for it to happen over here, on the other side. And then the cycle would happen. It depends on how quickly that happens. By studying the stellar evolution, it helps astronauts understand the history and future of galaxies, the formation of planetary systems, and the conditions necessary for life. By observing stars at various stages of life cycles, scientists can piece together the complex puzzle of cosmic evolution. Now we're beginning to understand it, we're learning more and everything like that. It's getting more and more and more. We're understanding more and more. However, we're still taking baby steps. We've got a lot more to learn. We're only at the beginning. And by learning more and doing more, we will get this. Hopefully you can help this. So this is sort of where my notes sort of end now. So we come to our conclusion. As we conclude our exploration of the life cycle of stars, it is clear that celestial objects are the fundamental to structure and evolution of the universe. They are the building blocks. Without them, there are no more stars. There are no more planets. We need them to go through this cycle. From birth in stellar nurseries to the dramatic end of the supernova, or a white dwarf, or a black dwarf, or a neutron star, they play critical roles in shaping the cosmos. Understanding, and this is true, understanding the different stages of stellar evolution not only enriches our knowledge of astrophysics, but deepens our appreciation for the dynamic process that govern the universe. Because we're still trying to understand dark energy and dark matter. Supernovas, neutron stars are helping us map this and understand it because it shines a light on it. Stars, the light of stars is a testament to the interconnectedness of the cosmos events and the ongoing journey of matter through space and time. Remember, these things do spread out and they do take time. So I thank you for joining me on this cosmic journey. I really hope you enjoyed it about the life cycle of stars. We will keep going. The next episode will be on our sun, our dynamic star. I really hope you tune in and listen to it, and I hope you enjoy it. Please send your questions in, please like, share, and keep listening. And don't forget to look up. Take care.